Friday, you're starting.
So, you know from last exercise, when we found the critical value, the minimum, maximum, any of those, the moment I recognized where the critical value was, I pretty much knew the shape of the graph. Yes. So with practice, it'll come to you. Also, without a calculator, you can actually know what it's going to look like. But there are a few tests that one can do to determine the shape of the graph. And they are related to each other. Sometimes you just need one of the two tests to determine the shape. And sometimes you would need both. So it is a matter of case. So the two types are the first derivative test. And the second derivative test. Of course, the test must use derivatives, right? It's a given. So suppose we have a function.
Is there going to be a second derivative test? Oh, there is.
So let's say we have a function f of x. The test follows a simple set of rules. First, you find f prime of x. Number two, you set f prime of x equal to 0 and solve for x. What does that solution give you? What? Slope.
Critical value.
Oh, critical value. So that is going to give you the critical value. It could either be a real number or it needed to exist. So and oftentimes it happens when we have, I mentioned this when we were talking about critical values. Then we have a critical value which corresponds to local minimum or maximum, but the critical value doesn't exist.
Isn't it when it's a straight line?
Straight line, okay.
A
A sharp turn, right? If you have something like that, that's a cutback from it. Sharp turn. So any one of those cases, you end up having a critical value that doesn't exist.
So wait, what are the cases for that again? Cusp and.
Cusp and sharp turn.
Or a cusp slash.
I'll do this for illustration so you can understand it better. So let's say the critical value is C. What is the derivative at C? Let's see if we can put 2 and 2 together.
So since it's a straight, are we talking about this as if we're imagining an imaginary function, or are we talking about this as if it's just a straight line? Because if it's a straight line, then the critical value would be every single point.
We're not talking about straight line, we're talking about any function, and I'm going to tell you that C is a critical value, and I want to know what the derivative is, the value of the derivative at the critical value. 0.
I was just simply asking, is the most I can put out.
So now we pick two test points to the left, one to the left, one to the right. Easy ones. Let's say the critical value is 1. Don't pick 3.719 as a test value. That's ridiculous. So pick an easy test point to the left and to the right. And we have to plug that in the derivative, first derivative. If that is greater than 0, so when you plug in the first derivative, you're going to get a number. And if that number is greater than 0, the function, the original function, is going up. Because we know a positive derivative would imply a positive slope, so the function would be increasing. To the left, or to the right of the critical value, if it is less than 0, then the function will be decreasing. Yes. Now that I've got that bit of information, in this case, since there is a term, there is going to be a local minimum or maximum from the curve that I just drew, or the nature of the curve. Does f of x have a maximum or minimum? So this is talking about, the test is talking about the behavior of the original function. So that's how the function behaves. Going closer to the critical value, then it goes that way. Does it have a maximum or minimum? Maximum. So just by looking at this, I know that there is a maximum. Also, is it concave up or concave down? Up.
Up? Oh, me down. Tony down.
Up.
I'm thinking of up like that, but.
It's a matter of perspective, yeah, I guess. It's concave down. So I determined the nature of the function as to whether it is increasing or decreasing. And I also knew that the function is going to be concave downwards.
Will you ever have it where f of like x of 1 is like less than 0 and it'd be the other way?
Could be. That's my next step. So can I erase? So you pick two test points, x1, x2, plug it in the derivative. If the derivative is less than 0, the function will be decreasing. Derivative greater than 0 at the test value that you pick, the function is increase. Good. Does this have a minimum or a maximum? Minimum. Another way to verify if you actually have a minimum or a maximum, when it exists, is to take the derivative and plug in the critical value. When you plug it in, the second derivative, if it is bigger than 0, then
So you either use first derivatives by having 2 points next to it and see the direction that they go. Or you simply take the second derivative of, at the very least, f of c, and then from there you can tell whether it's going to correspond to a minimum or maximum.
No, not necessary. We could come to that conclusion using the first derivative.
No,
That's it.
that's what I'm
Just
saying.
by graphing, but what I'm saying is an alternative would be to plug it in the second derivative. And if that value is bigger than 0, we'll have a minimum.
So
Likewise, over here, if it is less than 0, the point is a max. Whatever interval that we explain has to be within the domain of the function. That is a given. It has to lie within the domain of the function. So are we clear? So just by looking at this behavior, one can determine whether the curve is where it's increasing, decreasing, if it's concave down or concave up. Sometimes, if we have more than one physical value, the concavity will change. For instance, we copy this. Yes.
Is that the second derivative C?
No, the second derivative of the function evaluated at C. Like you plug in C in the second derivative. Can I erase this time?
So effectively, if the second derivative of f of c is greater than 0, then that means that corresponds to a minimum, meaning it's concave up. If it is less than 0, that's going to concave down, and it's going to be a maximum.
Provided there is only one local minimum or maximum. So, as I mentioned, you can determine the behavior of a function on any interval just by looking at the first derivative. We don't even have to go to the second derivative necessarily. Sometimes one would wonder as to why things change when you have more than one maximum or minimum. So let's say that's my function. Yes, and it is concave up in certain intervals, concave down in other intervals. So clearly the function changed in concavity at some point. Do you agree? Yes. Now, at what x value did the function change in concavity from concave down to concave up for the first time? Or right here? It changed, correct? So where did it change?
In the middle.
How do you know if it's right in the middle? It could be right here.
Well, yeah, that's like what I'm saying, like in between those 2 points.
Definitely, right? So it could either be there or there, correct? I can't simply justify as to where that inflection point are. I just threw that word in or phrase. So where that point is, the point where the concavity changes. The point where the concavity changes is what we call an inflection point, or the point of inflection. So it would either go from down to up or up to down. Again, Geo said it's going to be somewhere here, but we just don't know where. But what is going to tell us the exact location of that point of inflection, the second derivative? In some cases, the point of inflection may not exist. Just like the critical value, the point of inflection may not exist.
So, sir, would this mostly just be used for data analysis?
Yes,
So this wouldn't be used for something like engineering?
it will be used that too.
Really? How does this apply to like a physical example?
If you want to say. Then going back to, physics. Let's say you have an ellipse, the elliptical orbit, that's in 2 dimensions. Let's say you reduce that to a 1-dimensional curve, and you want to know where a particular planet or satellite or whatever changed its direction, right? Exactly, the exact point. And you can get that using secondary. So it is easy for us to simply look at parabolas and cubic functions because you guys are just learning. But in practice, especially in physics and upper-level math, there are cases where we want to extend this concept to something more complicated. For instance, you can visualize up to 3 dimensions. And if I asked you, could you visualize a 4-dimensional object? A 5-dimensional object? Technically, how many dimensions could one come up with? 99. Those are the problems you have. You don't get it?
Oh.
Are you guys too young to know that?
No, we know the joke.
Okay. So, where was that? So how many dimensions could we have? Infinite dimensions. Technically, there are infinite dimensions, but even from a theoretical standpoint, if you want to say, find the maximum of a particular point in 5 dimensions, you can't just visualize, you can't use your calculator to come up with the answer.
You need.
That's where this comes into play.
So what exactly, like, why exactly do we want to calculate 5 dimensions? How do we even know 5 dimensions are possible?
But dimensions are always possible. Think about a very simple case of data analysis, on the slides. So let's say you are measuring the risk of cancer. Okay, and that is your response value. And then the risk is associated with age, gender, whether you smoke or not, blood pressure, cholesterol.
So dimensions is variables.
Each of those variables, just like the XY plane. You have 2 dimensions, X is a variable, Y is a variable. You have the 3-dimensional plane, X is a variable, Y is one, Z is another. So you can come up with infinitely many variables, so infinite dimensions.
It'd be interesting when eventually 3D graphs become.
What?
No, I'm saying I'm saying at the very least with software turning out, but just 3D graphs.
3D is the maximum that we can. Okay, so if you want to find that point of inflection, so you find the second derivative. Set that equal to 0. When you set it equal to 0, the solution that you have will be the point of inflection. It can be a real number, or it just may not exist. So typically, the point of inflection doesn't exist in cases where you have cusps or something like that. For instance,
So you weren't, at the very least, finding, let's say, f prime of c and then just taking that sector, instead you're just.
you can do f prime of c. Typically, we do the first derivative, then move on to
I thought it would be mandatory to do it from c for it makes no sense when you think about it.
So that function is what we call a sorted function, right? Here clearly the first derivative is not going to exist there. And the second derivative test will fail in this case, not because it doesn't exist, but because it will become zero. The reason being, no matter what point you pick over here, it's always the second derivative will always be zero, because the first derivative is a constant. It corresponds to the slope of this line. The derivative of a constant is zero. So if you can't find the second derivative and you're setting that equal to zero, well, which point is it? Every single point would equal zero, right? So that is a case which would present a problem. What type of discontinuity do we have? Infinite discontinuity at that point. I'll just call it C. What happened to the concavity? It's partially opening, but sort of is going this way, right? So it's open up. Over there, it's going that way. It's open down. It doesn't have to be a proper turn such as that. Even partially open is good enough. So clearly the concavity changed, but that is not a point where the derivative is going to exist. Right? So that is a case where we have a point of inflection that will not exist. So we have to test for critical values. We have to test for places where we would have asymptotes to determine concavity. So now that we've got the point of inflection, the process is exactly the same as we did previously with the first derivative test. I don't want to call C, I'll call it M. M is the point of inflection. What is the value of the second derivative at the point of inflection?
Zero.
Zero.
Because it's the point at which it starts turning.
Changing concavity.
Oh, sorry, but you go on.
So pick a test point, an easy one, to the left and to the right of the relevant line about the point of inflection. Plug in that value in the second derivative. And if that value is less than zero, then the curve is concave down. If that value is greater than zero, then it will be concave up. So it can go from concave up to concave down to concave up. but could it be a possibility where sort of looking weird, what do I mean by that? Here is an example. Do we understand this part? How to test? Here is an example. Right? So, where did the concavity change? Or did it change?
It changed.
Did the concavity change? Well,
Like
No,
right.
how does it work?
right here somewhere, correct. So the concavity perhaps changed there and there.
Can it change in 2 places?
Yes, it has to make a test change. But will the first derivative exist somewhere here? No. Or yes? Will it exist? Yeah, but what is the value of that?
Zero.
Zero. The second derivative, would it exist? Yeah, but it will be zero. It wouldn't give you information. So those are weird cases where we've got to be careful about determining concavity. Same with these functions where you have discontinuity, sharp turns, cusps, and so forth. Are we clear? So sometimes you can come up with the shape of a curve just with the first and second derivative. Sometimes, just with the first derivative. Sometimes you will need the second derivative. What is the purpose of the first derivative test? It gives you intervals where the function is increasing or decreasing. The second derivative test will give you intervals where the function is concave up or concave down. Good. The most common mistake that beginners will do in first derivative test and the second derivative test is, instead of plugging in these test points in the first and second derivatives appropriately, you would by nature plug that in the original function. Right? Because all these years, oftentimes when you evaluated something, habitually you would evaluate the original function, f of x or h of x. But you should not plug this in the original function. Second derivative test, you have to plug the test points in the second derivative. First derivative test, you have to plug in the test points in the first derivative. Good? Now, after all these years, I have made that mistake occasionally. So be careful. Are we clear?